In 1976, Amtrak operated 150 brand-new locomotives that should have been the solution to America's passenger rail crisis. Instead, they became the center of a federal investigation. The SDP-40F, built by Locomotive Division, was involved in a series of derailments that forced regulators to act. Within 5 years, every single unit had been removed from passenger service. This is the story of how a locomotive class designed to save Amtrak nearly destroyed public confidence in rail travel entirely. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. When Amtrak began operations on May 1, 1971, it inherited a catastrophe. 20 private railroads had dumped their passenger operations onto a quasi-governmental corporation with almost no funding and equipment that belonged in a museum. The locomotive roster was a nightmare. Aging E units from the 1950s, hand-me-down F units, even a few Alco PAs that broke down weekly. Nothing was standardized. Maintenance was reactive, not preventive. Amtrak needed modern power immediately. Locomotive Division offered what seemed like a perfect solution. The SD-40-2 had become the standard freight locomotive across North America. Railroads trusted it. Parts were everywhere. Delivery times were short. EMD proposed a passenger variant. Take the SD-40-2 platform, add steam generators for heating passenger cars, and deliver it fast. Amtrak, desperate and underfunded, ordered 150 units in 1973. But there was a problem baked into this decision that no one fully understood. Passenger service operates under fundamentally different physical demands than freight. Freight locomotives pull heavy loads at moderate speeds, often 40 to 50 miles per hour. Passenger trains run light consists at sustained speeds of 70, 80, even 90 miles per hour. The physics change completely. EMD had built thousands of successful freight locomotives, but translating that success to passenger service required more than adding steam generators and a different paint scheme. The steam generator requirement itself created complications. In 1973, most passenger cars still use steam for heating and air conditioning. Head-end power systems, which generate electricity for the entire train, were not yet standard, so the SDP-40F needed to carry a boiler, fuel for that boiler, and approximately 1,800 gallons of water. That water alone weighed over 7 tons. All of this equipment sat above the locomotive's frame, on the roof and in the body, raising the center of gravity significantly compared to a standard SD-40-2. Amtrak had no choice but to accept the compromise. The railroad was hemorrhaging money, public confidence was eroding, and Congress was questioning whether passenger rail should exist at all. The SDP-40F promised reliability, parts commonality, and immediate availability. On paper, it solved every problem Amtrak faced. The SD-40-2 was engineered for one purpose: moving heavy freight trains efficiently. Its 6-axle CC truck arrangement distributed weight across more contact points, providing superior traction on steep grades. The rigid 15-foot 6-inch wheelbase on each truck handled the weight of coal hoppers and grain cars without issue. At 30 or 40 miles per hour, with thousands of tons behind it, the SD-40-2 was stable, predictable, and nearly bulletproof. The SDP-40F retained that entire structure. Same frame, same trucks, same wheelbase. EMD added the steam generator, water tanks, larger fuel capacity for the boiler, and additional electrical equipment for passenger service. The modifications increased the locomotive's weight from approximately 368,000 pounds to around 410,000 pounds. More critically, they shifted the weight distribution upward. The vertical center of gravity on a standard SD-40-2 sat relatively low, close to the frame rails. Freight locomotives are designed this way intentionally. Stability comes from keeping mass near the rails. The SDP-40F placed thousands of pounds of equipment above that baseline. The steam generator sat in the car body. Water tanks were positioned high. Even the electrical cabinets were roof-mounted. Every modification raised the center of mass. This wouldn't have mattered at freight speeds. At 40 miles per hour, track irregularities pass under the locomotive slowly enough that the suspension can absorb them. The trucks follow the rails, the springs compress and extend, and the locomotive remains stable. But passenger trains don't operate at 40 miles per hour. They operate at 70, 80, sometimes 90 miles per hour on the same track that was built for slow-moving freight. At those speeds, the same track irregularities that a freight locomotive absorbs become dynamic events. The six-axle configuration presented another problem. In freight service, more axles mean more traction. In passenger service at high speed, more axles mean a longer rigid wheelbase that responds differently to track geometry. A 4-axle locomotive with an 8-foot 6-inch wheelbase per truck can navigate curves and elevation changes more fluidly. The trucks articulate independently, following the rail profile. A 6-axle locomotive has to bridge longer sections of imperfect track, and when it encounters curves, crossovers, or worn rail joints at speed, the rigid wheelbase fights the geometry instead of conforming to it. The water in the steam generator tanks added a final variable, fluid slosh. At low speeds, this sloshing is negligible. At high speeds, especially in curves, the movement of 1,800 gallons of water becomes a dynamic mass that shifts the locomotive's balance in real time. Engineers call this phenomenon liquid cargo effect. It's why tanker trucks have baffles. The SDP-40F had water tanks, but they weren't designed with the assumption that the locomotive would be cornering at 70 miles per hour. Static testing revealed none of these issues. The locomotive sat level on shop tracks. Weight distribution met specifications. Brake tests passed. The units were cleared for service and began hauling Amtrak's premier trains: the Empire Builder, the Southwest Chief, the California Zephyr. For the first year, everything seemed fine. The first incidents were attributed to track conditions. In 1975, an SDP-40F-led train derailed in Indiana. Investigators found worn rail and inadequate ballast. The locomotive was cleared. A few months later, another derailment occurred in Illinois. Again, poor track conditions were cited. Amtrak's infrastructure was decades old, maintained on a shoestring budget. Derailments were not uncommon across the railroad industry in the 1970s, but a pattern emerged. The derailments kept happening, and they kept involving SDP-40Fs. Not every time, but often enough that Amtrak's operations staff began noticing. The incidents occurred at moderate to high speeds, usually between 60 and 80 miles per hour. They happened on curves, on uneven track, and on sections where rail joints had settled unevenly. Most critically, they were not caused by mechanical failure. The locomotives weren't breaking, the brakes weren't failing, the wheels weren't cracking. In several cases, the locomotive remained on the rails while trailing passenger cars derailed. In other cases, the locomotive itself went off the track, dragging equipment behind it. The inconsistency made the problem harder to diagnose. If the SDP-40F were fundamentally flawed, it should fail predictably. Instead, it failed situationally. Railroads that hosted Amtrak trains began complaining. The Burlington Northern, Santa Fe, Union Pacific, all of them reported that SDP-40F-led trains were rougher on their track than other equipment. Some railroads quietly asked Amtrak to use different power on their lines. The Federal Railroad Administration took notice. By 1977, the FRA had documented over a dozen incidents involving SDP-40Fs. None resulted in fatalities, but several caused injuries, and all of them disrupted service. Passenger rail was already fighting for survival in the United States. Public perception mattered. A derailment, even a minor one, made national news. Amtrak couldn't afford the headlines, and the FRA couldn't ignore the pattern. What made the situation particularly frustrating was that no single cause emerged. Investigators examined wheel profiles, truck alignment, suspension components, and brake rigging. Everything met specifications. The locomotives weren't defective in the traditional sense. They were built correctly. They passed inspections. They operated within tolerances, and yet, under specific conditions, they destabilized. The root cause was vertical load dynamics. At high speed, a locomotive doesn't just roll on the rails, it bounces, rocks, and shifts in 3 dimensions. The suspension system is supposed to manage this motion, keeping the wheels in contact with the rail even when the rail itself is uneven. But that system is tuned for a specific set of assumptions: weight distribution, speed, and track quality. The SDP-40F violated those assumptions. When a freight locomotive encounters a dip in the track at 40 miles per hour, the suspension compresses gradually. The springs absorb the energy. The weight of the locomotive, most of it low and centered, pushes back down, keeping the wheels firmly on the rails. The system is over-damped intentionally. Freight railroads value stability over ride quality. At 80 miles per hour, the same dip becomes a dynamic event. The locomotive hits the irregularity faster than the suspension can respond. Instead of compressing smoothly, the springs compress and then rebound. If the center of gravity is low, the rebound energy dissipates into the frame. If the center of gravity is high, the rebound energy translates into vertical motion, bouncing. The locomotive lifts momentarily. The SDP-40F, with its elevated center of gravity, responded to track irregularities by oscillating vertically. The motion wasn't dramatic. We're talking about inches, not feet. But at 80 miles per hour, a wheel that lifts even an inch off the rail loses lateral stability. The flange is no longer guiding the wheel set. For a fraction of a second, the locomotive is skating rather than rolling. On perfectly straight track, this might not matter. The locomotive would settle back down. But American track in the 1970s was not perfectly straight. Rail joints were staggered, not welded. Curves were frequent. Crossovers were common. Every time the SDP-40F encountered a curve while oscillating vertically, the combination of centrifugal force and reduced wheel contact created a destabilizing moment. The six-axle truck arrangement amplified the problem. With 3 axles per truck, the lead axle would encounter the track irregularity first, followed by the middle axle, then the trailing axle. Each encounter sent a wave of energy through the suspension. If the timing lined up poorly, if the track irregularities were spaced at a frequency that matched the suspension's natural rebound cycle, the oscillations compounded. Engineers call this resonance. The locomotive would begin to hunt, rocking side to side as well as bouncing vertically. The water in the steam generator tanks made everything worse. As the locomotive rocked, the water sloshed in the same direction, shifting the center of gravity dynamically. The effect was similar to a person trying to balance a bucket of water while walking a tightrope. Every movement of the bucket requires a compensating movement of the body. The SDP-40F suspension couldn't compensate fast enough. There's a reason modern passenger locomotives are 4-axle designs with low-mounted equipment. The F40PH, which replaced the SDP-40F, weighed less, sat lower, and had shorter truck wheelbases. It wasn't more powerful, it was more appropriate for the physics of passenger service. The Federal Railroad Administration launched a formal investigation in 1978. They conducted dynamometer tests measuring the forces acting on the track as SDP-40FS passed over instrumented sections. They compared the data to other locomotive classes operating on the same routes. The results were clear. The SDP-40F generated higher lateral forces and vertical loads than comparable power. The margin wasn't enormous, but it was consistent. Amtrak faced a political and operational crisis. The railroad couldn't publicly admit that its newest locomotives were problematic. That would undermine confidence in the entire system. But it also couldn't ignore federal investigators and host railroads demanding action. The solution was a quiet withdrawal. There was no formal ban. The FRA never issued an order prohibiting the SDP-40F from operating. Instead, Amtrak announced a fleet modernization program. The railroad would purchase new F40PH locomotives from EMD, a 4-axle design specifically engineered for passenger service. The F40PHS would have head-end power instead of steam generators, eliminating the water tanks entirely. The transition would be gradual, and the SDP-40FS would be reassigned or sold. By 1981, most SDP-40Fs had been removed from Amtrak's roster. Some were sold to freight railroads, others were stored. A few remained in commuter service briefly before being retired entirely. The official narrative was fleet standardization. The actual reason was that Amtrak and the FRA had quietly agreed the locomotives were unsuitable for sustained high-speed passenger service. The irony is that the locomotives themselves were not inherently dangerous. They were the wrong tool for the job. A perfectly good hammer makes a terrible screwdriver. Southern Pacific Railroad purchased several SDP-40FS from Amtrak in the early 1980s. They were cheap, relatively low mileage, and used proven EMD components. But Southern Pacific didn't want passenger locomotives, they wanted freight power, so they rebuilt them. The steam generators were removed, the water tanks were stripped out, the roof-mounted equipment was replaced or relocated. The locomotives were reconfigured as standard freight units, redesignated as SD-45RS. The weight came down, the center of gravity dropped, and they ran reliably for another 15 years in freight service. This proved what engineers had suspected. The SDP-40F wasn't a bad locomotive. It was a poorly adapted one. Remove the passenger-specific equipment, lower the center of mass, and it behaved like every other EMD 6-axle unit. The problems Amtrak experienced were not mechanical defects. They were the predictable outcome of running a freight platform at passenger speeds with an elevated center of gravity. The SDP-40F revealed a fundamental truth about passenger rail that the American industry had forgotten. passenger and freight locomotives are not interchangeable. They operate under different physical constraints, and those constraints demand different engineering solutions. Freight locomotives prioritize tractive effort and durability. Passenger locomotives prioritize stability at speed and ride quality. Europe learned this lesson decades earlier. European railways developed dedicated passenger locomotive designs with low centers of gravity, short wheelbases, and sophisticated suspension systems. American railroads, focused on freight, assumed they could adapt freight platforms to passenger service with minor modifications. The SDP-40F proved that assumption wrong. The locomotive Amtrak was forced to walk away from wasn't banned because it was dangerous. It was removed because it demonstrated that passenger rail requires purpose-built equipment. The F-40PH that replaced it became one of the most successful passenger locomotives in American history, precisely because it was engineered from the ground up for the speeds, loads, and track conditions of passenger service. The SDP-40F's legacy is not failure. It's a lesson in physics, and that lesson is still relevant today as Amtrak and regional carriers plan the next generation of American passenger rail.